more kind of background knowledge, but let's try to get through as much as we can. So, announcements. So, the mid-semester project has been released and it's due next Monday for class. And there will be no lecturing during next Monday's class, but class will become check off. And there'll be no discussion this Friday because of CalHacks. All right, so here's the agenda for today. We're going to first talk about what are APIs, how can we make network calls using those APIs, and then finally we're going to talk about what is Swift concurrency, that those concepts also include async await and how we handle errors for functions that throw an error. Again, these are a lot of new concepts, but I'll try my best to kind of describe them in a simple way as possible. So APIs stand for Application Programming Interface, and it simply state a set of rules and protocols that allow for different software applications to communicate with each other, and most importantly, to exchange data. And it's basically code that abstracts away some of the internal details that that function does, and it gives you an endpoint where other people, your app, whatever, can interact with it from the outside. Okay, and we've seen them before. So, for example, in SwiftUI, we have worked with view modifiers and also different types of SwiftUI views, right? For example, the image view, right? We don't really care about how an image is actually represented, right? In the more kind of nitty-gritty details. We just use an image and we just pass in that system image string for as a symbol, or maybe you have an asset that you have imported into project, and you could just basically refer to that asset name and load it up as an image, right? We don't care about the actual concrete details of how an image, how SwiftUI represents an image, right? We just use the image view and we can modify it using view modifiers, right? And for example, in Swift, we have arrays, and there's a bunch of methods that call an arrays. For example, the count is empty. We can get the first element and get an optional of that element type, right? So that an API for arrays are all this, all the properties and also all the functions that we can interact with a Swift array, and those are and that's an API basically. Most commonly, you will interact with APIs with a client and server paradigm. So a client is something like an app, or for example, your phone, or in this case, our app, right? And we want to get information from some server or database. And you can think of this analogy like, for example, Instagram, right? The Instagram app, when it launches, it makes a request to the Instagram server. And that server returns some response. And usually that response is, you know, pieces of data that we could use. And we could, you know, process that data locally and show it to the user appropriately, right? So it's kind of request and response paradigm. Now on the server, we have, it probably exposes some functions for the app to call from, right? For example, you give it the user, it fetches all the images for that user, right? Um, if the user updates their user profile image, you give it the new image, and the server updates it on its end. Maybe you want to fetch the latest posts within a certain time frame, and we get the data back. So the server exposes this API, right? All these different functions and abilities that we could interact with the server on our end, right? That allows us to interact with on the client end. And the reason for this is like, well, as an app, we don't really care about the details or internal details of how we actually fetch an image on the server itself, right? Maybe, for example, maybe this is what happens on the server itself. So when we pass in the user, right, maybe it goes to a cache, maybe it saves frequently requested images in this cache. It goes there first to see if it has images. If not, we go to the user or the database row for that user. and then it gets all of the user image IDs, um, maybe it's stored on that row, and then actually retrieve it in the database itself and return it out, right? Well, on the app concern, it doesn't need to know all about this, right? So this function abstracts it all away, all of these details from us, and just gives us this endpoint for us to call from, right? And yes, the actual implementation is hidden. We only interact with the function itself. Now, here is, again, this is the Swift Array API, as mentioned earlier. And here are like different properties, right? How do we create an array, or how do we access or interact with the array by accessing its elements, right? So this whole documentation is the API. It provides us an endpoint or interface for us to interact with the array without actually needing to understand and know how an array is actually being implemented under the hood, right? So it abstracts all of the low-level details of what an array makes an array and just gives us these kind of endpoints for us to interact with. Cool. So hopefully that gives you a sense of what APIs are. Um, Now let's talk about how we can make networking calls. So there's three steps. One of them is you create a URL object. The second is you retrieve data from the URL via URL session. And the third is you decode data using, you decode the fetch data into a Swift struct or class object using something like a JSON decoder. So the first step is to create a URL object. And a URL stands for Uniform Resource Locator. And what that does is that it identifies the location of the resource. For example, we have seen URLs from websites, right? And that kind of uniquely identifies that page for the website. And actually, all these URLs, or all the web pages that you actually go to, go to your web browser, all of the pages are actually files located on some server or some remote computer. And that URL kind of uniquely identifies the file path for that file. And then also we can also refer to local files using the URL. So for example, like an app like GoodNotes. All the different documents in a GoodNotes app, that is most likely cached and saved locally on device. And the app probably, has a URL for that file and retrieves that local file from that URL. And so how do we create a URL in Swift? Well, we basically give it a string, right, for the URL string, and then we basically, using this constructor, we construct an instance of URL. So this is what it looks like in the code. So here we have the URL in this constructor, and we pass in that URL string as an argument into the string parameter, and it returns an optional. And if you remember, an optional is either has a value or it does not, or it's nil, right? So one way we could unwrap this optional is using a guard statement. So what this basically says is that if the URL is not nil, we unwrap the value and we assign it to this local variable called URL, and that we could reference it after any code after the guard statement. But if it's nil, we jump into this return case and then return out the function because this URL is invalid. Okay, so now let's talk about uh, actually the response, right? How's data formatted? And if you actually type in this URL, and this is an API where we get like random poetry, random poems. And if you enter this into your web browser, for example, Safari, we get this kind of response. And this is formatted in this data format called JSON. And as you can see, JSON is predicated on this key and value pairing. So we have a key and we have a value. It's basically a dictionary, right? So here we can see we have the strict title, and that is associated to a value, which is the title of this poem. And then here we have author, the author name, and so forth. So JSON stands for JavaScript Object Notation, and it's basically a lightweight, human-readable text-based format for storing and also exchanging data between a server and an app. And the data is structured in key and value pairs. So objects themselves are enclosed in these curly brackets, arrays are enclosed in square brackets, and each key value pair is separated by commas. And so go back to your client server paradigm. We have a client, we created our URL object. Now we need to actually make the request to the server. Now, how do we do that? Well, we use URL session. So URL session is the object that coordinates a group of related networking data transfer tasks. And the API of URL session is a bit complicated. There's a lot of different versions that you could perform network requests. There's abilities to observe states. So for example, when the networking request is happening, it can send callbacks to you and you can observe if it's like going well or not. But the function that we're going to be most concerned with is this function called data for delegate. And what this does is that it takes in a URL object and it returns this tuple. So it returns some data and it returns some URL response. Now, the data here is of type data. And so in Swift, the data type is simply like binary, ones and zeros. This URL response is this kind of response that we get from this function, and it simply has kind of fields for the status of this URL or this networking request, for example, status codes, if it succeeded or did it fail, or other kind of data that's packaged within here that might be necessary for if we're doing more complex tasks. Um, so okay, so we create a URL and we have called URL session.share.data to actually make the networking requests. Now there's two keywords here, try and wait. We're going to talk a bit more about that later, but for now, just you can ignore them. So we get back data in binary, in this data, in the Swift data type. And the data that's being encoded into binary is actually in the form of JSON, right? But from our perspective at this moment, it's just binary, it's just one and zeros. And we can't really interact with the data from, as a binary perspective. So our goal now is to basically decode this data type, which is currently binary, into like a Swift struct or class that we could use within our app. So here again, here's what the JSON looks like. Currently, it's wrapped within this array. We have a single object, and this is our poem. And you can see we have four different properties: title, author, lines, and line count. We want to convert this into a Swift struct. So we could represent this JSON as a struct, like you see on the right-hand side. So the struct poem has four properties: title, author, lines, and line count. And it directly maps to the keys in our JSON or encoded JSON on the left-hand side, right? Um, and to make the conversion or to convert or decode this data type or this data object, right, which is again it's JSON, but it's currently in binary format. To convert that into a struct home instance, we could use something called a JSON decoder. So what JSON decoder takes in is two things. It takes in the data, the encoded data in binary, which is the type data, and it also takes in the type that you want to decode that data into. So uh so we could pass in this data into JSON decoder, and we could say, hey, I want you to decode this data into a poem. And as a result, we can get a poem instance that we could actually utilize within our code. So again, the goal here is to map these four properties into the properties of our poem and create a poem object. So let's take a look at how we could use JSON decoder in the code. So all we need to do is create a JSON decoder instance, and then we call the decode method on that instance. And again, it takes in two arguments. The first argument is the type that we want to decode into. Remember that dot self on a type is, again, it's simply saying the type. And then the second argument is you're actually passing the data, so the data type. The data that we get back from URL session.share.data. And then the result that we get back is an instance of type poem that we could access as properties. For example, we do decoded poem.author and get the author. Okay, so now let's talk about what is Swift concurrency. And before I kind of get into that, we need to talk about how code kind of gets run on in relationship to the operating system. So this is a really simplified view of the kind of the stack of all of your apps and then your hardware, right? So these are all of your apps that are open on your iPhone. And then the bottom layer is the hardware. So like for example, I guess your CPU, your GPU, your all of your storage, right? Your SSD or whatever. And the operating system is the layer that sits between all of your apps, right? Your software and the hardware. And what it simply does is that it allocates resources for those apps, right? Memory, and also it does a lot, and it also kind of figures out what task to run on the CPU, right? And so it does a lot. It's like the middle manager between hardware and software, and it kind of orchestrates all of the different properties and things that, make your iPhone run. So let's take a look at the operating system. Now, how an app is actually represented in the operating system itself is through something we call processes. And so it represents an app as a process. Now, an app can have multiple process. Uh, a process is comprised of, again, there's different things, but one of them is kind of like a pool of threads. Now, how I like to think about threads is like you think of like a highway, right? Each thread is a highway lane. Now, on a highway lane, we have cars that run on each highway lane, right? We have, each lane has cars that go through one by one. The analogy for cars in our case is pieces of code, or basically chunks of code. And so you can imagine we have multiple threads, right? Multiple highway lanes, and our code are like cars that run on each lane. And then what happens is that the operating system chooses a thread or chooses a highway lane. And basically, once it chooses that thread, the code that's queued up on that lane, one by one, will be ran on the CPU. So in this case, it chooses the first thread, and then it takes the first code that's queued up and runs it on the CPU, right? And then it takes the second next one and it runs it on CPU. And then it might now it says, okay, now let's actually move to the third thread. So the operating system can choose which thread to run on. And so now it chooses the third thread, it runs that code in CPU and so forth. Now, the problem here is that let's say we have a bunch of code here, right? But one of the code segments is actually how we perform our networking task. Now, the issue here is that we don't know how long this networking task will take, right? Because it's predicated on a bunch of different conditions. Either, let's say your phone is in a really bad networking area. Let's say the device hardware itself, they're working, maybe the Wi-Fi protocol is using something like Wi-Fi 4 or something instead of, I think now it's like a Wi-Fi 7 or Wi-Fi 6E or something. Or maybe there's something on with the server, right? And the server has some issue that it's very slow to kind of process data, right? And return the data back. So this task right here, right? This piece of code, we don't know how long it's going to take. It's probably going to, in a good time, a good day, it might be, a couple milliseconds, or I don't know, like 100 milliseconds. But if it's on a really bad scenario, it might take multiple or a couple of seconds, right? We just don't know. And if you can imagine, right, our code, right, is like our cars. This is sort of like a truck, a really big truck. So when this networking task is queued up and it's ready to be run, right, that it might take a while before we can actually run any code later on. So this long networking task blocks the thread from actually doing meaningful work. What we can do is that we could suspend this networking task into a suspended state. And then while it's actually doing the networking, while we're awaiting for a response back from the server, we can actually free up that thread and run other code that the system queues up, right? We could run code that's related to different another app, right? Or we could run code that's running different part in a different part of your app, right? So we could free up this thread and we could run code and not be blocked by this networking task. And there is for example, there's a thread, a really special thread called the main thread. The main thread is designated by Apple, and it's a thread that all UI stuff should be on the main thread. So all the UI code, Swift UI, whatever, that's all done on the main thread. If you have networking things that are on the main thread, it's going to block UI code from actually running. So when you scroll, right, for example, when it's like, you have a list and it's like fetching the networking task, it might stutter, right? It might have what we called hitches, where it's blocked by this networking task and it's trying to update or refresh the screen for the UI, and it's not able to complete it in its designated time. And when that happens, we get hitches or kind of stutters on the device, which is not good. So instead, um, again, once this networking task is finished or resumed, we could bring it back down to the thread and we get some result back, and we could queue additional tasks to run as well. So this uh, basically unblocks, suspending the networking task and then resuming it allows us to free up that thread to perform other tasks that the system deems necessary. Okay, so now let's talk about how do we kind of code this suspension and resumption of these first, like a specific function, for example. And that kind of deals with these two keywords in Swift called async and await. Async stands for asynchronous. So we use async to mark as a function as synchronous. So again, when you see async, that is referring to the function declaration, right? We're declaring this function is asynchronous. What does it mean for a function to be asynchronous? Well, a asynchronous function basically it can start a long-running task. It's able to be suspended, which allows other code to run without waiting for the task to complete. And it's able to, once it's finished, it's able to resume that function on that thread it was originally on. Or I think it could also be on a different thread. Um, Now we use async in conjunction with await. So whenever you see async, you gotta think about await. When you see await, you gotta think about async. Okay, these are two kind of inseparable things. Await is a keyword that we use when we're calling asynchronous methods. Okay, so it's used together with async. And again, it's used at the call site. So fetch random poem is an asynchronous function. To call an asynchronous function, we have to use the await keyword. Now, whenever you see await, that is simply stating, okay, it should tell you that at this moment, this line, that denotes a place of suspension and resumption. So, okay, the code, runs sequentially, right? Once hit this function, the thread that this code is on, it could suspend this function at this point, right? Fetch random poem does its own thing. Okay, it's like fetching, right? In the meantime, that thread, the operating system can queue up other things to run. Now, once fetch random poem finishes, right, it goes back on, it resumes, and then it continues all the code after this line. Now, we've we can only call asynchronous methods in an asynchronous context. All the code that we've seen so far is synchronous. So how do we create a, or how do we, you know, create an asynchronous context within a synchronous context? We use this thing called task. So we create a task, and within this closure, right, within these two curly brackets, we have it creates an asynchronous context where we could actually run and perform asynchronous code. So what this happens is that the code goes for, and it goes on top and it runs some synchronous code, it comes to this task, and then it basically schedules this block of code to be ran on some future point in time. We don't know when, right? So one path is that the bottom synchronous code after this task declaration can actually be ran before the code in the task actually gets ran. Okay. So, we're running here. Okay, okay, okay. Synchronous code. All right. Here's the task. We schedule the code within this task, right, as to be ran on some future point of time. And then we keep on going, right? So again, this code might get ran first, then this task. So the execution order isn't guaranteed. So you got to think about this as like this task, it's like its own thing, this own block of code that's kind of separate from everything outside of it. Okay. And one thing I want to mention is that after this await is resumed, right? If you have other code after this line, it will then get ran. So again, if you have code after this line, right? The code once we're in this task, right? Once this is ran, it will suspend. That thread that this code is in could schedule other things or other tasks. And then once it resumed, all right, we get this poem and then it executes code sequentially afterwards, right? Okay, so next let's talk about how do we handle errors. So similarly, like we have async and await, there's also two other keywords that are similar to async and await, and they're also coupled. And that is throws and try. So a function could throw an error, okay? And to denote a function can throw an error, we use this throws keyword. And if your function is also asynchronous, you have to put throws after async. Um, and a function does not need to be asynchronous to be throwable. You could also remove this asynchronous. So it's a synchronous function that also throws. When a function throws an error, that error is propagated up the call stack. So for example, let's say I have a function that calls this function fetch random poem. And for some reason, here, and fetch random poem calls URL session.share.data, right? That URL session.share.data also throws. So let's say, we're trying to make a request to the server at a given URL, and that fails. URL session.share.data will return or throw an error, and it will throw it back up the call stack. So who called URL session.share.data, which is fetched random poem. So the error is propagated back to fetched random poem. And since fetch random poem is throwable, it will propagate that error back up to whoever called fetch random poem. Now, eventually, we'll walk up the chain, right? And eventually we have to handle that thrown error, right? So how do we handle the error that's being thrown, right? We use something called a do catch block, and we'll take a look at that at two slides later on. Okay, so similar to await, right? When you call a throwable function, right, the call site needs to be marked with try. So when we call it a asynchronous function, we have to use the keyword await. When we call a throwable function, we have to use the try keyword. So in this case, at this line, we have let poem equals try await fetch random poem. What this line is telling me is that fetch random poem is asynchronous because it has the await keyword, and it also throws an error, right? It's able to throw an error because of this try keyword. And what's weird is that for async and throws, in the function declaration, async comes first and throws comes second. But when you actually call it, try comes first and await comes second if you use both, right? So it's kind of flip-flopped a little bit. Okay, so like I mentioned before, at some point, propagated error needs to be handled. And to handle or throw that, if an error is thrown, we need to handle it. And to handle it, we use a do catch block. So a do catch block has two parts, the do part and the catch block. So the do part is where our code gets ran. So here we have these two lines right here. And we have, the first line is where we actually make a request given a URL. And the second line is where we try to decode that fetch data, right? This is a data type, of type data, and then decode it into a poem struct. Now, as you can see, Euro session can throw an error, right? Let's say, something went wrong during the networking request. Maybe, oh, um, our network or we accidentally got disconnected from Wi-Fi, right? And it's not able to make this it's not able to complete this request. So it can throw an error and then catch that error in this catch block. So basically, if this throws an error, we do not go to the next line. We basically go directly to this catch block. And this catch block has this variable, it's kind of like implicit that we can get called error, and we could access its properties, or maybe there's a description of this error. And this is the place where you might throw an error, or show an error to the user, say, hey, maybe something went wrong, maybe you want to try again. So you could recall this function recursively to try to perform this networking request again. Now let's say if this line succeeds, right? Okay, then we move on to the next line where we do the decoding. And again, this is throwable because what if the data that we get is like is badly formatted, or maybe in our struct or poem, one of our properties is did not we accidentally did it was a typo, right? Maybe added it was in it, all of the properties needs to match the ones from our JSON for the JSON decoder to match it one to one, right? But if it's not able to do that, if I have a typo in one of my properties names, then it's not able to do that. Instead, it's going to throw an error. So yeah, and so if it does throw an error, we catch it here in this block, and we can do error handling as we see fit. Okay, so let's do a quick demo of actually implement this in the code itself. So here we have our project, and it's a very simple project. Here we have a content view, and with just a button here, where once we press on this button, we'll or we call our fetch random poem method, and that method is located in our view model. So here, as you can see, we have our poem struct, and as you can this is, I forgot to mention, but we need to conform our poem struct into this decodable protocol. And when you conform an object or into or struct or class, whatever, to be decodable, what that means is that you could pass it into something like a JSON decoder, and it's able to automatically decode the data object into this struct poem or a class, okay, automatically. And one of the requirements is that if you conform yourself to be decodable, all of your properties also need to be decodable. So here we just have like an array of strings and strings. By default, strings is a primitive data type in Swift, and they inherently are decodable by default, and arrays as well. So we don't need to do anything. But if you have custom data types that you have embedded here, you need to also mark them as decodable. Okay, so here we have this function called fetch random poem, right? And I'm just delete this first. Okay, the first step, remember, is to create our URL. Um, Let me actually get back this the URL. So let me just copy this real quick. Ooh, it's complicated. Okay. And then let me just go back. Okay. So the first step is to create our URL. So what we do is that we do let URL, and then we pass in the URL string as an argument. And then since this returns an optional, I'm gonna unwrap it using this guard syntax. And here we're returning if it is nil. And since this function returns an optional poem, we have to return nil. Okay, so that was the first step. The second step is now to actually make the request using this URL. So to do that, we use URL session dot shared dot data, and we're going to use this version of it where we pass in this URL. As you can see, it's asynchronous. It throws and returns a tuple with the first element in the tuple as our data, which is basically JSON that we get back from this endpoint as JSON, but it's in this data type format, and we get this URL response. For our case, we don't need the URL response, so we just ignore that and just get the data. So we're gonna call this function, and we're gonna pass in that URL instance that created or unwrapped, right? Okay, so now we get many errors, right? We see we have call can throw, but it's not marked with try, and the error is not handled. And also we get expression is async, but it's not marked with await. So again, URL_session.share.data is asynchronous and it throws. So we need to, since it's asynchronous, when we're calling this function, we need the await keyword. And since it throws, we need the try keyword in front of the await. Okay, so now we can unpack the tuple, and we could do that using this syntax. We could basically have these parentheses, and then we could unpack the two elements in the tuple as variables. So I'm going to get this as data. And a convention when you're writing code is that if you're not using um, if you're not using, for example, I'm not using the URL response field of the tuple. And to denote that I'm not using it, usually people write this underscore to say, hey, I am ignoring this field. Okay. Now I should get another error saying that errors thrown here are not handled, right? Because here this has a probability, or it might throw an error, but we need to catch that error and handle it. So to handle that, we use the do catch block. Okay. So again, the code that we run is located in this do closure. And then here in the catch block is where we actually can catch that error if it throws an error. So for now, we can, just print a simple print statement saying, hey, error occurred or something. And then we use string interpolation to print the error out. Okay, so that's our second step. Our third step is to decode our data and convert it into this poem type and get a poem object out of it. So I'll create a JSON decoder, an instance of it, and we call it decode method. And it takes in a type, right? A decodable type. And say, hey, I want you to decode into the poem type. We use poem and then dot self. The dot self is how we get to basically say the type of this struct or a class if you have a class. All right, and this from arguments, sorry, a parameter, we can just basically pass in that data as the argument. Decode is a throwable function. As you can see here, it throws an error, or it's able to throw an error. So to call this function, we need the try keyword. And here we could say decoded poem. Nice. So now this function right here returns a poem. So all we need to do is that we could return the decoded poem out. Okay. Now, one thing here is that if we go back to the JSON representation, you can see in the most outer layer, we have these arrays. So the JSON, the most outer layer is actually an array of objects, right? These curly brackets indicate an object or each poem. So what we need to do is that we're not going to decode into a single poem, but we need to convert the JSON into an array of poems. To do that, we just basically use the syntax where we could wrap the poem into, using these square brackets to denote an array of poems. And so since decoded poems now is an array of poems, I want the first random poem that I get out. And to get the first element of an array, we can use the first property of an array, and that simply returns an optional of the array type. All right, there we go. Nice. Okay, so let's head back to our content view. And here in our button, let's actually call our poem. Oh, sorry, call and fetch random poem function in our view model. So let's do view model dot fetch random poem. And as you can see, our fetch random poem is async. So when calling an asynchronous method, we need the wait keyword, and then we can get the result back by assigning it to random poem as a private state variable of this view. Now, the issue here is that all of this code is synchronous, right? But remember, when we're calling an asynchronous function, that needs to be within a asynchronous context. So to create a now in a prior, here in this in the function, um, we can mark this function as asynchronous, right? But here in a content view, right, we can't, there's no function for us, or there's no enclosing function for us to mark as async. So we're already at the root, right? We're already at the very top. So we need to create a new asynchronous context from scratch. And the way we do this is, remember, we use the task, we create a new task. And then within the closure of this task, we pass in all the asynchronous code that we want to have, and which is basically calling wait um, vmodel.fetchRandom. Okay, so now let's take a look. So here in this 50 canvas, let's click on this and see what happened. So there we go. So we can see that we have um, we've done a network request to that endpoint, and we decoded it into an array of poems, and we're getting the first poem. And here we're assigning it to the state variable. So now when it changes, if we have dependencies within our view, it will update accordingly to reflect the new value of random poem. And in this case, we're putting out title, putting out author, and we're putting out the line counts. And if you want, you could also use a for each, loop over random poem.lines, and then print them out as text. So that is a quick tour of how you would integrate, or make a networking request, and how you would use it within your app. So usually you want to have all of your networking code separated into your view model. You shouldn't have networking code in your views. Again, separation responsibility. Your views should only be views, right? Nothing else. But our view model is where we do a lot of our business logic, right? Where we might have variables that pertain to the state of the app itself, as well as networking stuff. Now, in more complicated apps, you might want to abstract all of your networking stuff into another class, like a networking manager, and have that as an instance that you create, and then you inject it into your view model that you could use. But again, for what we're doing, it's a very simple app, right? So we put our networking code in our view model for now. Um, yeah, and that's basically today's lecture. So yeah, hopefully, again, there's a lot of content. I know there's a lot of different nuances and a lot of new things, but hopefully you have a better idea, and you get the bigger picture of how we make network requests. And once you look at this a bit more, once you review the slides a bit more, the actual implementation is actually really, it's very concise, right? This is like 10 lines of code. And so yeah, with still concurrency, it's you're able to write this in a very clean way that just kind of really makes sense. So yeah.